Our research falls within the field of knowledge representation and reasoning, or KRO, which is an approach to AI which focuses on representing information about the world and reasoning about this information. This project will use propositional logic to represent information. Propositional logic uses propositional atoms, which are just sentences which can be assigned a truth value. That is, they are always either true or false, and Boolean operators to represent statements. We use 5 distinct Boolean operators, each with their own meaning. For example, the statement P implies B could be used to represent the statement that all penguins are birds. We refer to these composite statements as formulas. A knowledge base is a set of formulas. We can infer new information from a knowledge base which is not explicitly stated in the knowledge base. For example, if we have a knowledge base that consists of 2 formulas, P implies B, meaning penguins are birds, and B implies W, meaning birds have wings, then from this knowledge base, can conclude that penguins have wings. This form of reasoning, which allows us to infer new information from our knowledge base, is known as classical reasoning. Now, consider the knowledge base consisting of the formulas penguins are birds and birds fly. From this, we can conclude that penguins fly, but we know in the real world this is not true. Consider the same knowledge with the added information that penguins do not fly. We now see that from our knowledge base, we can conclude that penguins both fly and do not fly simultaneously, which is a contradiction. This means that penguins cannot exist, but we know that penguins do exist. This is a limitation of classical reasoning. We require a framework for knowledge representation that allows penguins to exist as a bird, yet not fly. That is, a framework which supports reasoning in the presence of contradictory information.
Defeasible reasoning is a type of reasoning that allows for statements of the form typically A implies B, or in this case, typically birds fly. This form of reasoning supports the concepts of typicality, as in, given the above statement, a typical bird is able to fly, as well as exceptionality, meaning ostriches and penguins are birds which cannot fly, however, they can exist in our world without causing contradictions. This is because they are merely exceptions to the above assertion. So we are now able to represent the information, but given that the word typically might mean different things to different people, reasoning about this information is not unique. For example, prototypical reasoning is very conservative and is apprehensive about drawing too many conclusions from our knowledge base, whereas presumptive reasoning is extremely adventurous and tries to infer as much information as possible from our knowledge base. Consider the following example. We are presented with the information that penguins are birds, birds typically fly, birds typically have wings, and penguins do not fly. And we are asked, so typically, will a penguin have wings? And the answer to this is, it depends. Presumptive reasoning would say yes, because penguins are birds, birds typically have wings, and we haven't been told any information to the contrary. Prototypical reasoning, on the other hand, would say, well, yes, a penguin is a bird, but it doesn't fly, so it's not a typical bird. So we assume that any statement made regarding typical birds does not apply to penguins. So no, penguins won't typically have wings. So what is the problem that our project aims to solve? Currently, there is no propositional logic defeasible reasoner, which is a computer program which allows us to reason according to these reasoning techniques. There are algorithms to reason about defeasible knowledge bases. For presumptive reasoning, the approach is known as lexicographic closure, and for prototypical reasoning, it's known as rational closure. But, given that there's no implementation of them, there has been no research done regarding how efficient an implementation of these algorithms may be. Lastly, there are no defeasible knowledge bases we can use to test the correctness and efficiency of such an implementation.
The SCADR project was divided into 2 parts. Joel and Daniel each implemented a different algorithm for defeasible reasoning, them being rational closure and lexicographic closure respectively. They also identified and implemented heuristics in order to optimize their implementations. A defeasible knowledge base generator was constructed by myself, Aidan, for testing and evaluation purposes. This included identifying useful parameters that were used in knowledge-based generation relating to different aspects of scalability testing with respect to the implementations. KBGT is a Scala-based knowledge-based generation tool. It comprises an implementation of propositional logic with data structures for knowledge bases and propositional and defeasible formulas, as well as services for things like classical entailment checking and computing the knowledge base ranking algorithm BaseRank. The key purpose of the tool is parameterized knowledge-based generation. This is done through a graph-based procedure, of which a simplified example is shown on the right and is outlined in more detail within the paper. There is also a manual procedure for adding and subtracting individual statements to and from a knowledge base. The parameters that proved useful are the number of defeasible ranks, the number of defeasible statements, the distribution of defeasible statements over the defeasible ranks, and whether or not only defeasible statements should be used. Here is a small example of the usage of KBGT. We see on the left the help text that outlines how one utilizes the program, underneath of which an example of how to generate a knowledge base containing 5 defeasible ranks, 25 defeasible statements, and a uniform distribution of the defeasible ranks, ultimately being outputted to a JSON file named knowledge base. On the right, we can see the knowledge base generated adheres to the parameters we set, as well as the options available for interactive generation.
The rational closure algorithm works by ranking the statements in a knowledge base by how general they are, and removing ranks one by one from the top downwards until it's possible for the antecedent of our query to be true, and then checking if the remaining statements entail the classical version of that query. We used two different approaches to optimize this algorithm, which were using a binary search to find at which rank the antecedent of our query becomes consistent with the knowledge base, and the second approach was storing the rank numbers at which different antecedents become consistent with the knowledge base, in order to stop the same calculation from happening repeatedly. Our findings were that the binary search optimization was highly effective for queries where the rank at which the antecedents become consistent with the knowledge base is low down, i.e. a higher rank number, as naturally the linear approach would take an exceedingly long time to find a rank which is exceedingly low down. The rank storing approach provided excellent results where the same KB was being queried repeatedly with queries with the same antecedent, as we could simply retrieve the rank at which that query becomes consistent with our knowledge base via a lookup, and thus a lot of repeated computation was saved.
Lexicographic closure works similarly to rational closure. However, it is not necessary to remove every statement in a rank. Lexicographic closure removes as few statements as possible, by only removing statements one at a time until the premise of our defeasible claim is constant with our knowledge base. In our example, by removing the statement B typically implies F, the remaining statements entail that penguins have wings. Thus, we can conclude that penguins typically have wings using the lexicographic closure. Several optimization approaches were taken. We concluded that the optimization approach using binary search and ternary search performed the best, but we still wanted to see which search heuristics performed better. Thus, most comparison tests were made between optimizations using binary search and ternary search. The tests were made to compare the performance of the optimizations using binary search and ternary search. By inspection, it seemed as if the optimization using ternary search was performing better than the binary search. For the exact values, we averaged the total time taken, and for every test done, the optimization using ternary search outperformed the binary search. In our theory, we expect a worst-case execution time of 2 log base 2n for binary search and 3 log base 3n for ternary search.